like to thank the organizers for giving us a chance to speak here. This is my recent work, which appeared on Archive last month. So here's the conclusions of this talk. So I have two things that I want to say in this talk. So the first thing is kind of physical, and the second thing is some mathematical implications. So the first one is, I proposed a novel relation, GKB-Whittaker relation in AdS2 CFT1 correspondence. And this is physical. And the second one is the application. It's number theory. So I propose some conjectural relationship between some fundamental elements, the building blocks, in math and physics, which is a conformal dimension in physics, and also prime number in mathematics.
What are EN and ER?
Yeah, I'll explain later. Yeah. Yeah, but this is the energy of the balancing states. So most of actually the result is based on the analysis of the conformal quantum mechanics. So let me explain. So start with the definition of conformal symmetry in one dimension, namely the quantum mechanics. So the conformal symmetry in one dimension is defined by this transformation of time coordinates. So they contain three infinitesimal parameters, epsilon 1, epsilon 2, epsilon 3. And they are generated by Hamiltonian, the attention operator, and conformal boost generator. And you can show easily, so they actually satisfy the SL2 algebra. And we can identify one-dimensional, yeah, this is the definition, the one-dimensional conformal symmetry as the SL2 symmetry. So there are several analyses of conformal quantum mechanics so far, and the work is pioneered by these three authors, Dorafalov, Pini, and Fulran, and this is so-called the DFF model. And it is the simplest model. This is a one-particle model with inverse square-type potential. And also it contains some interesting model, which is an integrable model, so-called cultural model. And it is actually possessing such a pairwise interaction between each particle with inverse square-type potential. But most of the analysis so far are based on classical Lagrange description. So we actually assume action principle exists. And also the most analysis is focused on the discrete spectrum. Namely the discrete spectrum is kind of representative, so specific representation. So by my work here, so I'd like to talk about without classical Lagrange description and different types of representation of SL2R. So namely continuous spectrum. So let me review the representation of SL2R. So it is non-compact. So if you think about the non-trivial representation, so we have to think about the infinite dimensional representation. And they are characterized by some invariant characters. And so there are two characters. One is the central character, and the other is the infinitesimal character. And for the SL2R, we can, by using the Alexander automorphism, we can identify these characters with the plus minus as the central character, because the center of the SL2R is nothing but the cyclic group of order 2. And also, infinitesimal character can be determined by the Kashmir operator. So there are 4 series of the representation for the infinite dimensional SL2R. So for instance, so the simple model is the model. The analysis is basically as done for the discrete series representation. But in this talk, so I'd like to talk about the principal series representation, which corresponds to the continuous spectrum. And so the representation of n plus r, in more generic case, can be also has a Chevalier basis. So one of the useful concepts is Whittaker vector idea. So if we use define this Whittaker vector, we can construct such a representation or infinite dimensional representation. And in the case of conformal quantum mechanics, we take any for just one. And we can easily identify these generators, the Chevalier basis, with Hamiltonian, conformal boost generator, and the attention operator. So namely, so we can identify the energy eigenstate with the Whittaker vector. So in terms of Whittaker vector, I cannot explain today, but there are many applications in physics and math. So in today's talk, I want to talk about the quantum mechanics relevant to the application to black holes, two-dimensional gravity, and number theory. But they contain some other applications in math and physics. So now, let's come to the one result in my work. So the AdS2, one of the significant relation in AdS2 correspondence is the GKB-Witten relation. The statement is the d-dimensional CFT, the density function of correlation function d-dimensional CFT, boundary CFT, corresponds to the partition function, which takes value in the boundary varies. And so this is kind of a basic relation in AdS2 correspondence. So before going on, so I'd like to comment on the AdS2 1. This is exotic cases. So one point, what I'd like to say is that AdS2 1 is in some sense, the most important example, since for this particular property. So it has been shown that although the extreme of the biggest black hole contains AdS2 factor. So in that sense, if you understand AdS2 1 correspondence, we probably know some concept of AdS2 correspondence. And so there are several exotic features. So, but in today's talk, the excited states on the boundary, there are several evidence for such excited states on the boundary. And this is kind of relevant to this work. So, and also they, in CFM side, CFT1 side, so we have several exotic features. So the first result is this one. So the more precisely, so the left-hand side, the CQM side, the quantum mechanics side, is a generating function of the dilatation operator. But notice that, so here, EL, the first question, this answer is the energy of the boundary states. Namely, so that this energy is calculated as the eigenvalue of the other Whittaker vector. And right-hand side is a partition function of about AdS2, which is computed in terms of the Wheeler-DeWitt field series in mini-superspace approximation. So let me go on to detail. So the computation in quantum mechanics, for that briefly explain about it. So this quantity is defined as some particular function of psi here. And then I add the Casimir operator on this object. Then I can find the differential equations. And on the two-dimensional gravity side, we expect the theory is described as a Wheeler field theory. And it has been discussed in topological string theory, such a partition function for given boundary, we can compute. So the partition function can transform as a wave function. So actually, in the Wheeler series, so if you take the mini-superspace approximation, which is taking only the zero moves, we can find this particular differential equation as a wave function. So at this stage, we can see that these two equations are nothing but Wheeler-DeWitt equations. So we have dictionary compared with these two equations. And I think so, if this dictionary is correct, so we can lead off the AdS2 radius can be controlled by the energy of boundary state. So this is kind of relevant to the fact in the AdS3 CFT2 case, the central charge actually control the AdS3 radius proposed by Brown now. So, and one observation from this, if you take the energy of the boundary state equals to 0, namely the ground state, and also consider some classical regions, so B goes to 0, it suggests L2 goes to infinite. So in some sense, so ground states might correspond to the flat space. So I think so this is some conceivable suggestion. So we cannot find such a relation in AdS2 CFT1 for the ground state. Yes?
So I'm confused about something basic. At the beginning you said you're using the continuous series representation for
Yes.
the So I thought that these representations were labeled by some real part and an imaginary part, and they didn't go all the way down to zeros. The eigenvalues of the
So what did you
operator
mean by
half.
the imaginary and real part?
I thought that the eigenvalues of L0 are half plus is or something like that in the continuous series.
No, so the
Is that the eigenvalue? Yeah. How does that
Uh,
relate to EL and ER? The eigenvalues of EL and ER?
so it's the character of the representation.
No, I'm just talking about the highest weight or the lowest weight, the eigenvalue of the lowest weight. The character is that in a sequence of descendants,
Yes.
but just the eigenvalue of the lowest weight I thought is in the continuous series is half plus is.
Yes. So you mean that half is the real part.
That's right.
Okay. So yeah, the third part is the imaginary part. That is the imaginary part that characterizes characters.
But I mean, how is the eigenvalue of the energy of the Hamiltonian related to this half plus is? You're saying the imaginary part of that is somehow the.
So this energy is not relevant to the character.
The character that appears the highest weight is not related to.
Is not related. The characters is correspond to the some conformal dimension of the state.
Oh, I see.
Yeah. So then, I'd like to expect the result quantity can give us some expectation values, nothing but this quantity. So, but this quantity is computed among excited states. So what is the physical meaning of this? Well, so this is the second result, I thought. So looking at, so this actually gives rise to the conformal dimensions of the states. But in other aspects, I actually propose this can tell us some information of prime number. So let me explain about that. So actually the computation, the resulting computation of this, but I should explain what is the meaning of this delta and how to compute this object. And actually here is nothing but symptomatic behavior of the counting function of the Riemann zeros. So in order to explain this, so I'd like to begin in some mathematical deep problem, namely the Riemann hypothesis. So this is one of the Hilbert 23 programs, the 8, so the number 8. And also it is listed as a Millennium problem. The statement of the Riemann hypothesis is that so all the non-trivial zeros of the zeta function are complex number with the real part half. So as we mentioned, the real part is half. And so this is the uniquely series representation. So but we can also represent in terms of the Euler product representation. And here, actually, it is kind of suggesting that so zeta function knows about prime number. So actually, Riemann proposed actually sort of this counting function for the Riemann, so the zeros of zeta function. And here, rho is a zeros of zeta function. And he actually proposed a conjecture, so the zeros of the prime number, number of prime numbers, is relevant to the zeros of zeta function. So this is a significant, some considerable importance of the Riemann hypothesis. So this is so-called the Riemann zeros. So in order to see, so that understand such a Riemann zero, there is other conjecture, the so-called Hilbert-Fourier conjecture. This conjecture states that the imaginary part of the eigenvalues, imaginary part of non-trivial Riemann zeros can be realized as the eigenvalues of some other self-adjoint operator. So this is kind of in physical application, is kind of actually, Perry and Keating and Alan Conner, the mathematician and physicists, proposed this generator as the Hamiltonian with the form XP. So you can easily see this is this actually cannot give rise to some discrete spectrum. This is not unstable system. But the interesting point is that if we compute in semi-classical analysis the number of states, so which is a phase space, XP phase space, so we can count the number of the states by computing the area of the phase space divided by Planck cell. And the significance is that so these properties, the behavior is nothing but a symptomatic behavior of the counting of the Riemann series. But this operator is not Hamiltonian, I would like to say. So in the simplest model of the quantum mechanics, different model, so this operator XP is identified with the dilatation operator. So I'd like to come back to the previous program. So what is the meaning of this? So I can compute this quantity because this actually satisfies the Wheeler-DeWitt equation. So I can compute exactly, so in terms of the Magnotta function. So Z is actually the some variables which actually correspond to the energy of the states. And also I take the limit where the energy goes to 0. So this function actually gives us some wave function, the eigenfunction. And also I take the limit, this eigenvalues big, so large. So the resultant counting of the function is given by this equation. And here we get same particular behavior for the counting function of Riemann fields. So again, so this is my conclusion. So in this talk, I'd like to show you some first relates probably example for the GT-DeWitt relation in AdS2 CFT1. And the other is some conceivable relation among the some fundamental building blocks in math and physics, Kohn dimension and prime number. So this is the final message. So quantum mechanics contains some application in physics and math. So let's study quantum mechanics. Thank you very much.
What was the interpretation of big lambda again?
Sorry?
What was the interpretation of big lambda again from the number theory perspective?
Yes, lambda is so the conformal quantum mechanics is defined. So it corresponds to the conformal dimension. But it is represents so in mass actually so in mass it corresponds to the imaginary part of the Riemann fields.
So are we talking about delta or lambda?
So the lambda is the character of the CFT1. Yeah.
So I'd like to ask about internal manifolds. So you did not consider internal manifolds here, right? So AdS2 only.
Yes.
So if you consider the internal manifolds, the result one should be modified, right?
Well, yeah, I think so. That if you think about the supersymmetric case,
but I think that the internal manifolds contribute to the partition function.
Which result you are claiming? So which result? So
Yeah, result one. So could you see the?
Yes, this one.
Yeah. GDS2. The right hand side.
Yeah, probably so. Additional symmetry can give some constraints on this relation. But if you have AdS2 factors, so like SO1, 2, because if you think about the super conformal algebra, so bosonic sector can be described this relation, I guess. But if you think about the supersymmetric factor, some PPS sector,